Now that we know how to find all those lovely t-values, we're going to have to apply them into the confidence interval formula for a population mean. I know you're excited. You've been waiting the whole section for this formula, and it's right here. And remember, just real quickly, this symbol up in the front, don't get confused by that. All that's saying is that your confidence level and your alpha are complements of each other. That's why it's 1 minus alpha. Right? And alpha, remember, is going to come up to us again and again in chapters 10 and 11 and, well, and 9. It's going to keep popping up. It's the area in both tails, or a single tail in chapters 10 and 11. All right. Now you don't have to memorize any of this because it's all in your exam notes packet. So when we look at the formulas right here, we're talking about this one right here. Right, so it's going to be a t-interval. You're going to use x bar plus or minus t alpha over 2 times s over the square root of n. Of course, s over the square root of n is an approximation of the standard error that we learned in chapter 8. Right? Now your point estimate is x bar. That's the center of your interval. And remember that the degrees of freedom is n minus 1. Now to be able to use this formula, we have to see if certain conditions are satisfied as well. Those conditions would be that we have a simple random sample, which is pretty typical for our course. We always assume randomness, which is actually quite tricky to get in real life, but that's what we're going with. Then we're going to assume we have independent sampling. Now, if you're sampling with replacement, if you keep putting the gumballs back in the machine or whatever, then you don't care. Independence is automatically there when you have with replacement. But without replacement, you need it so that your sample size is really small in comparison to the larger group. So imagine taking, I don't know, a sample of gumballs out of a machine. As long as you only take a really small sample, like 5 out of a machine of 5,000, it's not really going to affect it that much. That wouldn't really be a machine. That'd be more like a vat at the factory, but still, right? Just taking a few out from a huge amount isn't going to affect anybody upon this many pickpocket is made their livelihood, right? They just assume you won't notice. I steal a few candies from the big candy bin, no one will know the difference, right? Because they're assuming that visually you can't tell, right? But technically it's not true that it's independent, but we kind of fudge it and say, yeah, it's close enough, right? As long as your sample size is small, less than 5% of your population size, it's close enough, we'll count it as independent. And don't forget that if you're sampling with replacement, then, we don't even care, right? With replacement is always independent, at least for our purposes. Now, normal can happen two ways, and this is from the central limit theorem in chapter, well, all of this is sort of from the central limit theorem, but the normality is very important to us. We need the normal shape, not because you can use the normal curve, because you don't get to use the normal curve. You get to use the t-curve, but you can't even use the t-curve unless you know that the distribution is approximately normal. Now that can be given to you one of two ways. One, it can just state it somewhere. It's normally distributed. They'll write it somewhere in the paragraph someplace. Or they can give it to you in a graph, namely the normal probability plots that we learned about in chapter 7, where you have to look and see if the dots are between the boundary lines. Now, if they don't give it to you one of those two ways, then you have to have your sample size being greater than 30. And that should all sound very familiar to you because that's what we covered in chapter 8.1 with the central limit theorem. And just a little reminder, we don't know sigma, so we have to approximate the standard error with, right, remember SE is the standard error of the sampling distribution of, or standard error of the mean, right, it's x bar, right? So it's the standard error of x bar, and it's the S over the square root of n. And that's also why we're using t, because we don't know sigma as well. So we're kind of doing some approximations, some fudging, but it's fudging that works out very, very well, statistically speaking. All right, now here's how to find a confidence interval from raw data and summary statistics, but we'll see all of that as we do the problems. So let's do some problems. So we have, speaking of pickpockets, we have the FBI compiles data on robbery and property crimes and publishes that information every year. So we took a simple random sample of reported pickpocket offenses and it yields the following losses in dollars shown below. All right, so I have all these written out here. And the first thing it wants us to do is find the following and give 2 decimal places where necessary. Well, those symbols should look very familiar to you because we've taken exams on those. That's from chapter 3. That's the sample mean, the sample standard deviation, and the sample size, right, which are all statistics about this sample right here. So obviously I can count and tell you n is 30. That's not a hard thing to do, but the x bar and the s I want to be able to find. So I'm going to use my calculator to do it. So I go to Stat, I go to edit, and I type in all the values, which I've actually already done, but you type them in and clear out anything else. So I've got all those in. Then I go to stat, calculate, one variable statistics. It's been a while since we've done this, and L1, and then I go down to calculate and press enter. And there they are. I can see that the mean is 513.32. The standard deviation is the sample standard deviation because this was not a population. So I have to use the 262.23. And then the N is 25, right? Not 30, sorry, 25. There, and I just filled those three values into our answer blocks. All right, now what is the point estimate? What's our single best guess for how much people are losing when they get pickpocketed? Well, that's the sample mean, right? The sample mean is our point estimate because it's the single best guess we have for what mu would be, right? We're trying to guess what the population mean is, average loss. So that's our best guess for that. And that's what a point estimate is. It's our single best guess for what the population parameter mu is, right? But keep in mind, we don't actually think that mu is 513.32. What we think is that it's close to 513.32, right? So this is a statistic, 513.32, and we're guessing the parameter from it, parameter being mu. We don't think it's that, but we think it's close. How close? Well, that's what a confidence interval is going to do for us. But first, we need to verify that we have the requirements met in order to make a confidence interval. So you can't just go off willy-nilly making confidence intervals. You have to have reasons for doing it, or you have to have conditions met. So let's see if we've met all of our conditions. So the first condition was that it was a simple random sample, which it is more or less. We're a simple random sample of what's reported to the FBI. And I don't know if you noticed, but these are a lot of high numbers. And that's because in general, if you lose $26, you're not going to report it, right? As a general rule. So your only people that are going to report it are people that lost a lot of money. It's worth their time to report that they lost $844. Okay? But it does say right here, a simple random sample. So we're going to assume for our purposes, it's a simple random sample. Okay, so I typed that up. The simple random sample was given to us in the setup with that yellow part right there that I highlighted. So since it was given, fine, no troubles. Now the second thing is it independent? Now this is technically without replacement because they're not letting the same number. They're not letting 217 show up twice. At least we assume they're not because that would kind of be silly. But this is 25, but 25 is so far less than the 5% threshold of all the pickpocket offenses that we're going to call it independent, right? Even though it's a small number, or excuse me, it's a small number, even though it's without replacement, it's okay, right? Because it's far, far less than 5% of all the pickpocket offenses. This is kind of a hand wavy thing a little bit. It's a little bit like a magic trick, like ta-da, it is. But we do this a lot because usually our samples are so much less than all the possible population could be. And this population, obviously, there's a lot of pickpocketing going on in large cities, so this is way less than 5% of that. Right, and I realize that's a little bit weird, but that's all we're going to say about it. And sometimes we'll actually know the population number, so we'll be able to calculate it. But here we don't know it, but we can just assume that this is way less than 5%. And you have to write that. And the last but not least, do we have normal? Well, N is only 25, so that's a little bit of a concern. However, we have this lovely graph drawn over here to the right, which shows us that it is in fact normally distributed. So even though N equals 25 is less than 30, the probability plot, I'll just call it the graph. The graph at the right shows us that the data are normally distributed, as all the points are between those boundary lines. That was section 7.3, everybody's favorite section because it's so easy, right? You have to be able to look at a graph like that and know that it's normal, or the data are normal, I should say. All right, so we have 3 yeses. So that means that we are ready to go for making the confidence interval. So we have verified all our requirements. We've shown all 3 of them and given explanations and work for each one of them. All right, so now let's go construct that confidence interval. So we want to show the formula, the substitution, and the result in order to get all of our credit. Okay, so as we do this, let's keep a couple of things in mind. Our confidence level was 95%. That means that our alpha is 0.05 because they're complements of each other. Okay, I'll just make that a bullet. There we go. All right, so then since our sea level is 95%, that means that our alpha is 1 minus 95%, which is 1 minus 0.95, which is 0.05. There we have that. All right, that means that alpha over 2 is going to be 0.05 over 2, which is 0.025. Now, why am I doing all of that? Well, because of the formula. The formula, if I scroll back up here and get it, it's x bar plus or minus t alpha over 2. So in order to figure out what t alpha over 2 is, I'm going to need to be able to find alpha over 2, and that's what I'm doing. So I'm using what I know about the confidence level and the alpha to find my t alpha over 2, which is what we just spent a whole page practicing, finding critical t values. Right, so that means that my critical t value is inverse t 0.025 commas. Now my degrees of freedom, I better figure that out. N was 25, so that means that degrees of freedom is 24 because it's 25 take away 1. So df equals 24. And those two numbers, the alpha over 2 and the 24, are what I'm going to need in order to be able to find this value with my lovely calculator. So I'm going to use inverse t 0.025 comma 24. Okay, and that will be approximately some value, and I just have to find it. So let me go grab the calculator. Distribution, number 4, 0.025, 24. And I get 2.064. The negative doesn't really matter because I just need the number. I don't really need the plus or the minus, but nevertheless, right, that's the value that I need. You could also get it with the table. Let me show you that real quick. So it'd be 24 for your degrees of freedom. So you're going to move down to this row here. And then you want 0.025. And there it is, 2.064. So it's right there. Okay, so why did that help me? Well, because it gives me what I need for this formula. I now know that that t right there is 2.064. But I already found the other values. 25 was my n. This was 262.23 up there. Technically, that's a timesing, in case that wasn't clear. And this one's 513.32. We already found those values in part A. So they're all done. Now, you could sit there and type that into your calculator, or you could do the smart thing. When you look at how I did this in your note sheet, you'll notice that I actually tell you right here where to go on the calculator. It's the t interval right there. And I think I put it in the formula box as well in your notes. Right. Nope, I didn't, but that's okay. You can label it for yourself. It's the t interval right there. Well, I show it to you right here, that's why. Okay, so I'm going to make the calculator do the hard work for me of finding this result. So let's do that. So I'm going to go to Stat. I'm going to go to Tests. And now I want to pick number 8. If you look at number 8, it's t interval, which is what I want, right? So I grab number 8. And now we have a choice to make. So you could use data or you could use stats. So I actually have the data typed into a list in my calculator. So I'm going to pick data. So I moved the cursor to data and pressed enter. And I hit second L1 enter because that's where my data are stacked. Always leave frequency as 1. That's a more advanced topic than we cover. Our confidence level is 0.95 and I go down to calculate and press enter. And it runs the calculation. Oh, and isn't that convenient? It actually finds X bar, S, and N for me. Right, so if I hadn't run one variable stats for part A, it would have found them for me anyway. Nice, handy. So that gives me 405.08 and 621.56 is my result. And you're done, right? It's that simple. Use the calculator. So make notes. Use t interval. Right? Don't try to type that in by hand. Invariably, you do it wrong. Most students suffer with that. And quite frankly, the calculator didn't round. So it didn't round this t value out. It actually kept all the decimal places of accuracy. So that makes it very nice. Now, what does this confidence interval mean? Now that we know how to find it, well, we have to be able to explain it. So what this is saying is, look, if you took 25 pickpockets, 25 pickpockets, 25 pickpockets, you expect each one of them to have kind of a slightly different variation, but you expect the mu to sort of fall in them in those intervals you'd create 95% of the time. In other words, we are 95% confident that the true average of all pickpockets, reported pickpockets, I should say, is between 405.08 and 621.56. So you're 95% sure that the mu value, which is, and I explained what mu was, it's the true average of all the pickpocket offenses. Like, that's what that means. But you have to write it out in English. So you're 95% confident that the true average amount taken from all reported pickpocket offenses is in the US is somewhere between those two numbers. And give them units, of course. Units is always nice for a real problem. So if they have units, then use them. All right, now suppose a local law enforcement agent states that the amount of money for pickpocket offenses in his area locally is lower than the national average of 420. So just he claims, or with an average of 420. So he's saying, look, locally we're at 420. So that means we're lower than the national average. Well, you're lower than the national average. That's true because the national average is 513.32. But does this interval support or contradict his claim? And the answer is that the interval is between 405.08 and 621.56, but that does not support his claim of lower than. And that's because 420 is not lower than this interval. It's in the middle of that interval. Right? So that means that no, our interval does not support him. All right, so I typed that up. So his local area average was 420. He was claiming that 420, right, 420 is smaller than the national average, mu. But you have to compare it to the interval, and that's the key. So the interval is 405.08 to 621.56, and that does not support his claim, because to be lower than the average would mean that 420 has to be lower than your entire interval, and that is not happening here. 420 is within our interval. Now, how could this have worked? Well, if he had claimed it was the same as the national average, then our interval would have supported him, right? Because if he had claimed it was the same, then we would say, sure, right? Because 420 is in our interval, right? No trouble. If his average would have been 320, then we would have supported him as well, because 320 is lower than our 405 at the end, right? So you have to either be lower than the interval one way by changing your number, or you have to be saying, I'm not different, I'm just like the national average because I'm right there in the middle of it. The interval would have supported both of those kind of claims, but not that your average is lower with 420, because even though 420 is on the low side, it's still within the interval, and that's no good to you. It's within those interval limits. Now I'm setting you up here very, very strongly for chapter 10. What I'm doing right there is what you're going to have to do in chapters 10 and 11, and quite frankly, chapter 9 as well, right? So you have to compare the value to the interval. All right, we're all done with that one. I'll see you back here for example